Okay, so the lecture start now, yeah. So yes, I gotta share my screen. Yep, share my screen. Very important. Yep, okay, share my screen. Okay, you can hear me and you can see my screen, right? So correct, like everything's fine. Can you see me and my screen? Perfect. All right, cool. So let's go back to this one. Okay, so lecture recording is already uploaded like usual. So today we will focus on some of the lab for revising some of our math for derivative. And also we will talk about the recommendation system, right? This is a topic in machine learning and actually very related to our linear algebra and calculus. It can be very interesting. So our full-time class for machine learning, we have like final projects here. So we usually have a competition for them to like present their final project to see which one is the best. And then we invite all the judges from like different industry, especially machine learning, to join us and see which final project is the best. So far, I can see the trend that most of the winner for the final project using recommendation system. Yeah. So definitely this topic is very related. If you want to do something that's super useful, because if you think about right, all the e-commerce website right now in Vietnam, like Lazada, Shopee, Tiki, and all the big company like VNG, Yellow, they try to selling a products, right? And to sell that product, they need to target the customer, true. And to target the customer, they need to find a way to recommend what is the best product that can sell to this customer. Definitely need to find a way to recommend the products, right? So definitely recommendation system is a way for them to maximize the profit, help them to selling more products to the customer. So today we'll talk about the intuition and the basic concept of that, which is super useful because it's related to that product, which we learned that on Wednesday. Yep. So today we have two files, which is the lab and the lecture slide, okay? Before we are moving on to that topic, so yesterday we are already talking to this part about the computational graph, and the homework for yesterday is we need to finish the forward functions for sigmoid function and the backward function for sigmoid function. Just a reminder, sigmoid functions look like this, okay? This is a sigmoid function. So it's a very famous activation function in machine learning. But for now, you don't need to understand what is activation function. Just assume that this is a very normal function, yeah? So if I type in sigmoid, this is the function, yeah? So sigmoid is a function that it cut the vertical axis at 0.5 and then it tried reaching one here, but it's never reach one. But yep, this is the perfect example of sigmoid. So it's cutting the point here in the middle at 0.5. It tried to reach number one here, but it could never reach it. And the same thing with negative one here. So this is the sigmoid functions. So yesterday we already went through the example together, how to find the derivative for sigmoid function using the chain rule. I hope you guys remember that, okay? So we are trying to find the derivative. Instead of using math, we're using Python, using sigmoid functions. This is the compositional graph. So you can see that, let me draw something here. You can see that, so one, okay, so Z go here, become what? E negative Z, okay? And then plus one here, the whole thing here become one plus E negative Z and multiply by uh, 1 over x. So the whole thing here will become, uh, give me a second, double check. Yep. So it's gonna reverse the whole thing. So it's gonna be 1 over 1 plus e power z. This is the sigmoid functions. Okay, as you can see that this is how you calculate the compositional graph. So imagine that you have a variable z equal to 5, and you follow this graph, right, all the way here to the end. You calculate this special function, sigmoid. We call this a forward. Yeah, we call this one forward propagation. That means that you try to calculate the value of the f. And when you are trying to calculate the derivative of sigmoid function in respect of z, so we have to go backward, right, to find the derivative at any single step to the end here. We call that backward propagation. So there's 2 steps for you to follow. Definitely follow forward is easier because it's just like intuitive, right? But to follow backward, you need to do the chain rule and try to find the derivative at each section. Okay, let's do this part together. For the people who don't understand what I'm talking about, so please check out lecture recording yesterday. I think it's gonna be very important. Um, okay, this is the thing. Yeah, I just want to copy the solutions on the side for you guys to follow. Um, okay, perfect. So this is the how you calculate derivative of sigmoid function. Let me put it on the right hand side. Perfect. That is smaller. Yeah. The middle part is a super important part. Yeah. This is how you find the chain rule of sigmoid functions. Okay, so let's do it together. Remember our sigmoid function is 1 over 1 plus e to the power minus z here. So let's do the forward obligations. Um, so let's calculate this part first, yeah? So we can call an intermediate variable called a, yeah, it's a random variable, equal to exponential of negative z. This one will calculate what? This one will calculate e to the power negative z. Perfect. Now we want to plus them, so we can call another intermediate variable. So 1 plus a. Okay. So that's gonna calculate the the denominator of our sigmoid functions. Remember again, sigmoid function is 1 over 1 plus e to power z. Okay, so now we are calculate the bottom part already. Now continue to calculate the whole thing. So 1 over b. Does it make sense? So this one you calculate 1 to the power negative z. This part you calculate 1 plus e to the power z. This one you calculate 1 over 1 plus e to the power z. Okay, so this is how you calculate a forward propagations of these functions. And then you want to save this variable somewhere, right? So I just be saved inside the cage so that I can reuse them later during the derivative uh, part. So I can calculate the derivative faster using this um, cage variable. Because I'm gonna put cage inside my backward functions here. I can reuse them later on. Okay, that is how you calculate the forward. And to calculate backward, you need to follow the chain rule, right? So first, you can get out the a and b variable that we already set in the case. Yep. And later on, you need to calculate this part. Uh, Give me a second. I try to pull on the chat, but I can't see it because I'm on full screen or something. Yeah. So the exponential this equal to negative e to power z. They are the same. They are the same, but this one will be more accurate. The one I'm doing is actually more accurate. You can try. They are both the same. This should give you the same calculations. Okay. So first we will calculate this chain rule, yeah. Okay, let's do it together. So we want to calculate that chain rule. So dA equal to negative A. Why? Because I already say that the whole thing inside here is actually equal to A. Yeah, remember we already said the whole thing inside here is equal to this. So this one equal to negative A. Totally done. Okay, so this makes sense. Okay, let's continue with the next one. This is the next part. Yeah. So think about it. This one is the whole the the g functions actually equal to what? The g function actually equal to 1 plus h, yeah? So the derivative of g over h is equal to 1. That's perfectly correct. So db equal to da, yeah? We apply the chain rule here. So we like put them together, counting backward. Okay, and the next step we are doing this part, yeah? This part, this chain rule. So we keep going. So df equal to negative db over d power 2. Okay. Continue to apply the chain rule here to here. And based on this formula, we have negative 1 over g squared. So g is actually equal to b. So we can write down like this. That is why we need the variable a and b here, because we don't want to recalculate a and b. We can just like plug in here. It's just work. And then we want to return our df. This is our final derivative of f in respect of z. Okay, so we can try them. Let's try them. Um, so let's put z equal to 0. Okay, so my z0 equal to 0. That's perfect. Then I want to do forward first. I want to do forward first. Z0. Okay, I want to print out my f. Okay, let's try. Oh, I need to run the whole thing again. That is a bit annoying because I have to import the library of NumPy. Give me the error after initialize them. Yeah, okay, need to import the NumPy. Okay, should be good enough. Let's try that. Okay, 0.5. Okay, does it make sense? It makes sense. Why? Because when x equal to 0, the function here equals to 0.5. So our forward propagation working. What about our backward propagation? To find the derivative. To find that, you can do backward. X0, okay, you put case in, and I want to print out df. So this one is a derivative of f in respect of z at the position z equal to 0. Okay, let's print out the value and see what happens. 0.25. Okay, does it make sense? Let's pull out the graph. This is just the functions of sigmoid. We want to find the derivative vertive of sigmoid. Okay, this is the one. Let's zoom it. Let's zoom it in. I can open image in new tab. Okay, you can see that the blue thing is sigmoid and the red thing is the derivative of the sigmoid. You can see that at the position x equal to 0, the derivative equal go through 0.25. Okay, and that is exactly what we got, 0.25. Let's test out our function again. So when our x is a very big number, right? Z here. So what is the derivative of df? Can someone tell me that when z equal to a very big number or very small number, what is the derivative of f? Okay, let's have a look at the just the derivative of sigmoid only. This part, 0, that's correct. So can you think about, right? So derivative actually a tangent line. So at a very big x or big small x, you can have a very flat tangent, right? Like this or like this, right? And the slope of that tangent line is nearly 0, very close to 0. So you can try that. Yeah, you can try that. To, okay, if I have a really big number, let's say a millions, and I want to find derivative of that point exactly at 0, you can see that. Or I can find a negative 1 million, also not define a very small number, nearly 0. Yep. Okay, that's perfect. All right. So that is how you calculate the derivative of the sigmoid. And we use this computational graph to help us to do it. So the idea is very simple, just like how you do on paper, right? This is the chain rule. So if you don't understand this part, you should definitely go back and redo it. Okay. All right, let's quickly talk about the partial derivative today, okay? So what's the difference between partial derivative and derivative? So let's say you have a function f equal to 5x plus 3. So when you calculate the derivative of df of dx, right? So this one means that what is the derivative of f in respect of x? It means that if I increase x by a very small amount, how much f gonna change? So that is full derivative because for this function, we have only one single variable, which is x. That's why it's called full derivative. But let's say you have another variable, 7y plus a, for example. Then when you're doing derivative of x, of f in respect of x, it's not even a full derivative anymore, but it's actually a partial derivative. Yeah, because now we have um, two variable. So this is simple, yeah. To find the full derivative, you need to find the partial derivative of f in respect of x. And then you need to find the derivative of f in respect of y. And the whole thing here, we call that a full derivative. So df over dx. This is equal, but the, the x and y. So it's equal. So when you have multiple variables inside a function, to find a full derivative, you need to find the partial derivative of the function in respect of each variable. Okay, I hope it's straightforward. The term partial is like mean that it's a partly, it's not really full. It's not straightforward already. Therefore, we can call that a partial derivative. Okay, and this is exactly our linear regressions, right? So if you look at this, you think about we have n features, right? Remember in the Titanic, if we have multiple features of customer, each of the feature is ours. Could be like how tall you are, what's your gender, how much you buy a ticket, blah blah blah. That's your feature. And m is a m. M is number of samples in our data set, right? So this is one single row in our data set. This is like one single customer, right? Each of these one is a feature of that customer. So we have from 1 to n. And we plug it in our linear regressions. You can see that because we have W1 here multiplied by x1 plus x2 multiplied by W2 plus x3 multiplied by W3 plus xn multiplied by Wn plus d, that equal to our predictions, right? This is linear regressions. And you have like multiple samples or multiple row of that data set of trend set that you have multiple m row. This is one single row, this is one single row, and this is one single row. Okay. And this is the computational graph of linear regressions. In short, we can write this whole thing here equal to this matrix of our training set multiplied by the weight. Yeah, this way is the way of the hyperplane that we want to find. This is our x. This is the data we have already. This is the training set. This is the parameter we need to find to actually find the best linear regression model to fit our data. Okay, so if you multiply this, so this whole matrix multiplication equal to this row multiplied by that row, give you x1, okay, y1, our first prediction, y hat 1, and this row multiplied by this column give you x2, and then keep going until the last one multiplied by this column equal to x m. Okay, and that is dot 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 here. This is your full prediction. Each of these prediction corresponding to one customer could be like supply or not, right? Could be like what is the house pricing. So this is one single house, one single house, one single house multiplied by some weight, some parameters of our model, give you a prediction of the price of that house. House 1, house 2, and house M. That is like the whole idea about linear regression model. And in short, right, you can rewrite that. You have a weight and bias, so intercept, right? So you can rewrite this function like this. So wx plus b. So the whole thing here equal wx plus b, and this is the number of like data set, like m data set, m row in the data set. So we have m columns. And in short, this is the most important things. Mark them down. This is the most important things. So this is say that to the whole thing up here can define as the matrix function x. X is your training data, right? And then multiply by some weight parameter of your model, linear regression model, plus a bias, and give you y hat. I'm gonna write down the shape of the each of the matrix or vector for you, yeah. So who can tell me what is the shape of x? What is the shape of matrix X contain all the data of our training set? That's correct. So that's the M by N. What about W? What is the shape of W? Yes and no, right? So why is yes and no? Actually, N by 1. Okay. And then what about B? B shape. Okay, this one, 1. And then eventually you get back 1. M 1. Okay, this makes sense. So you have a data set with n features. Each, let's say each customer have n features, and you have m number of customer. So you multiply by a weight of parameters of your model in the shape of n 1. Okay. So after you multiply them, the shape should be m I 1. Okay. And then you plus bias, right? You plus one single bias, but you multiply by 1 you actually convert them into M1 to have the same shape. But the number B here won't change regardless the M here, right? So you have one single B only. So when you plus this, it's become M1. This makes sense because you have M customer, and so you want to have M prediction. Each prediction is for one single row of the data set. Yeah. So the whole thing here makes sense in terms of shape. Okay. Okay. So what is the derivative of uh of y hat in respect of w? Can someone tell me, please? What is the derivative of y hat in respect of w? Okay, you can imagine, right? So we have x1 multiplied by x1 plus x2 multiplied by xw2 plus dot until x n multiplied by w n plus b. Yes, correct. So the whole thing here gone. This is constant gone. So the whole thing here would be 1 plus x2 plus x3 plus xn. In short, it will be equal to x. Correct. Yes. Woohoo! You guys are the expert of derivative. Good job. Okay. That pretty much sum up the calculus for today. So we're gonna move on to something more interesting. Yeah, something like useful. Like, hey, this is cool, but can we have something like practical, something like actually like, oh, this makes sense in real world. Okay. So let's have a 2 minute break, okay? And then we're gonna move into the content-based recommendation. The lecture slide is in this uh lecture recording spreadsheet. You can check the lecture slide right here. So we might go through lecture slide and then we're gonna go through the lab for today. Very interesting for us. So let's have like 2 3 minute break. Also, why you already learned about this before? It's just like teaching in your IT class or like how do you know about it? Oh, that's pretty cool, yeah. So what is your position during the project at the time? Are you a project manager at the time for the project, or are you like working at like what? Oh, okay, interesting. Sorry, what's the major again? Mm. Yeah, this is my dinner. I'm having a mini cucumber for dinner. Pretty sad. You should come to go to school, man. You should take you should buy the air ticket and then come go to school. I'm gonna share dinner with you, man. Next time. Okay. Yeah, whenever you're free, okay? So when you have time, you can come like one day just to say hi. All right, so let's continue our lectures. All right. So today we're gonna learn about this pretty cool topic called recommendation system. Um, okay, sorry, why we actually won't study collaborative filtering today. We only focus on content based only. Uh, that's like solving my purpose. I just try to teach the basics of recommendation system. I don't want to go too deep into it. We might touch base again for recommendation system later on in the last few weeks of the course. Okay. Okay. Content based recommendations. Okay. Imagine that a user or you, right? You watching movies. So you can see that this woman liking the movie Shrek, and she was like dislike Harry Potter, Star Wars, and Mentor, Memento, right? This movie called Memento, and there are three movies. She haven't watched it. She haven't watched Blue. She haven't watched Dark Knight, and she haven't watched The Incredible, right? So she only watching four movie, and she disliked three of them. She only like this cartoon Shrek. So content-based filtering using item feature to recommend new item that's similar to what user like in the past. So this is pretty like common way how the company is selling stuff, right? So have you ever buy an items on Amazon? Yeah. So if you buy an item on Amazon, A- Amazon actually smart enough to like continue to harass you with a spam email of their marketing. You know, like, hey Tom, so you buy our book already, and you buy like Harry Potter book. We recommend you this other book, very also very interesting, and also some of the merchandise like toys of Harry Potter, this and that. So they have a very powerful system to predict what I like based on what I actually bought in the past. So that's the idea, right? And also, for these two movies, we also try to measure what is the similarity between two products or two movies. So, for example, The Incredibles, they actually have these categories: mystery, action, cartoon, comedy, and drama. While Shrek, right? They have the categories like fantasy, romance, magical realism, cartoon, comedy, and drama. So you can see that the similarity between these two movies are cartoon, comedy, and drama. This is how you calculate the similarity between two movies. So by now you already have like uh, think of a way how to recommend this woman of like other movies already. So the very intuition is like you actually calculate what movie are similar to each other, and based on what I actually like from the movie I watch, you continue to recommend me the movie that's similar to what I like in the past. That's the whole idea about it. So how do we do it with actions? So this is how you calculate, just like this is how you calculate two products, and this is how you calculate the similarity between two users, right? So you can see that there are two users and they have watching some of the movies in the past, And based on their history, you can see that there's a common ground between two of them. These two people actually watched these two movies before, which is Blue and Memento. Okay. So what is special about this? Okay, I'm gonna tell you. Um, so by now, everyone knows that Shark is actually a cartoon movie where it's kind of like fantasy, cartoon, happiness, right? Comedy. Incredible is like cartoon, comedy, and maybe sci-fi. These two movies are drama and depressions, all right? So this movie is about a woman who actually lost her husband and her daughter, and she actually spent her whole life in depression and trying not to suicide. This movie is Memento. This movie is about a guy who actually have a who actually forgot every day. Right? Who, every day he wake up, he just can't remember what happened to him yesterday, and his wife was murdered. So every day he have to find who is the murderer, but he just forgot information that he actually know yesterday. So he has to like tattoo the information on his arm. And every day he wake up and look at the mirror, like, oh my God. So this is what I did yesterday. And try to find a clue to investigate who's the murderer, right? So these two movies are like depression and drama and obviously sad. Anyway, these three movies like Star Wars, Harry Potter, and Dark Knight is sci-fi, it's kind of fantasy, it kind of actions, right? So you can see that they share a very similar taste in um, drama, the movie are drama. So there is a solution for that. So we have an embedding. Embedding is a map of our collection of items to a finite dimensional vector space. So what does it mean by that? So imagine that we have these three movies and we can map them into the vector. Right now, you see that all the knowledge we know about linear algebra are actually useful. We can map the movie based on its categories into a vector dimensions. And based on the vector dimension, you can calculate the similarity between each movie. So you can see that the Star Wars and Harry Potter, in the scale of fantasy and drama, they are near each other, and Memento was far away from them. So in conclusion, we can conclude that Harry Potter and Star Wars, they are similar to each other compared to Memento. This is just a two-dimensional space, but when you have, like, let's say, five categories, right, it's become five-dimensional space. So you can't really show that into a paper or visualize that. Then you can use dot product, right? This is why dot product is so useful regardless number of dimensions. Human can't see further than three dimensions, but to find similarity, so you can't really use visual to see it, but using dot product, you can actually calculate the similarity between two vectors. So that is really useful idea. Okay, so how you calculate the similarity between two vectors. So we already learned that on Tuesday. So the first way to do it is using a dot product, okay? Um, so a dot product is, this is a formula. So imagine I want to find the similarity score between Harry Potter and Star Wars. I can just multiply like this. So each of the elements of the vector multiply to each other, having the sum of them equal to 26. And the similarity score between the Star Wars and Memento is around 19. So definitely a higher score of similarity would mean that these two movies are actually more similar compared to these two movies. Another way to calculate similarity is using cosine similarity. And this is formula. So instead of using the dot product just like before, we are using this formula. So you multiply the two vectors together, but you divide by the length of these two vectors. So what is different between dot product and cosine similarity. Intuitionally, what is the difference? These two are kind of similar, right? It's trying to find the similarity between two vectors. But what is the difference between dot product and cosine similarity? And when you want to use dot product and when you want to using cosine similarity? Any question? Any suggestion? Yeah, in a way, yeah. So you can imagine that, let's say you have these two vectors. This is vector A, this is vector B. Yeah, so imagine this. A cosine similarity just care about the angle. You can see that it just care about the angle, how close they are, and that should be good enough. But a dot product not only care about the angle, how close they are, but also worry about how far they are, right? So in terms of cosine similarity, the cosine similarity between A and B, this B and A and this B are the same because they have the same angle. They don't really care about the scale, the length of the vector. But for dot product, these two are actually near to each other compared to this one. So when do we want to use cosine similarity and when we want to use dot product? So this depends on the applications, right? So a dot product could be huge, right? Let's say you have a very big vector with 1,000 dimensionals. When you do a dot product together, the n number could be huge, could be up to like a millions, right? But when you actually do cosine similarity, this gonna ranging from -1 to 1. Yeah, and that's nice because we don't really worry about if our like number gonna explode because we're getting too big for a high dimensional, right? So if you don't really care about the length of the vector, you want to see what is the angle, how different is the angle, then you can do cosine similarity. Um, for very small applications, these two gonna give you quite similar results. Yeah, so don't worry about it. You can use either one. But in this case, you can see that these two are the same. So the result of cosine similarity and the result of dot product in this case are the same. These two movies are still near each other compared to Memento. Okay. All right. We have a really quick quiz here. So compute the cosine similarity between Star Wars and Shrek and between Harry Potter and Incredibles. Which pair are more similar? Okay. Can someone do it? So between Star Wars, okay, between this and Shrek, or Harry Potter and Incredible. Okay, can you tell me which pair are actually near to each other? Okay, let's spend 2 minutes there. I want you guys to calculate the distance between this one and this one in terms of cosine similarity to see which one actually nearest to each other. Okay, so Wang Houcheng already say that Shrek and Star Wars is near. Okay. Any other uh, answers? Let's give people another maybe 20 seconds and then we're gonna move on. can you also tell me what is the calculation? What is the number for this pair and for that pair? Oh, what? Okay. So Star Wars and check is 0.66. Sure. Although 3 point. Interesting. Okay. Okay. Interesting. Oh, I actually didn't have the answers. All right. So this will be your homework. Yeah. You guys definitely can easily follow the where is it? You can easily follow this example to find the distance. I trust you, man. I trust you, Yui. Yeah. Uh, the answer may be based on you, may be on this. Okay. Let's double check that. We actually have a lot of things to cover today. Oh yeah, that's good. So let's move on. Let's assume this is the right answer. So everyone will double check on that. That's cool. That's good. That's the idea about calculating the distance or the similarity between two vectors. Okay, now it's like the main dish today, all right? This is today is like the main course. Okay, so imagine you are building a Netflix, the future Netflix, all right? And this is your website. So user watching these three movies. So Shark, Blue, and Harry Potter. And this is the ranking, okay? Note that. Okay. So he gives Shark 7, he gives Blue 4, and he gives Harry Potter 10. Uh, so the ranking was like between 1 to 10. Okay, and so it means that he very much like Harry Potter. He kind of like Shrek, and he not really like Blue. So based on this, okay, we have the this is the calories. You can say that this is the feature vector of the movie or categories. This is the calories of Harry Potter. So for Harry Potter, you can see that it's actually fantasy and comedy. For this cartoon, it's actually cartoon and comedy. For this depression movie, it's actually drama. And for other movie, it's actually like other categories. But you haven't watched this movie, this movie, this movie, this movie. Haven't watched it, only watching these three movies. Okay, so that is the user that we want to see. So the thing is, the question is, all right, he watching three movies already. We want to recommend him our movies, right? We have like 4 movies left to recommend him. So the question is, which movie do we want to recommend him? Which movie is the most likely that he's gonna like it based on all the movie he already watched? Okay, so let's remove all the movie he haven't watched it, right? Because he haven't watched it, then not really useful. So we only keep the movie he watched it. So only watching few movie, and this is his score, right? Um, this is his score 7, 4, and 10. This is the ranking vector. This is the matrix of a movie features right here. Yep. So after you multiply them together, you should have used a feature vector. What does it mean by that? So when you multiply a user, the ranking of a user to the movies, right? So imagine you multiply this together, and this together, and this together, and you sum all the calories up. It's gonna give you one single vector. Okay, it's perfect. So you multiply these two vector together, you're having this back, right? You can see that now we know that for the movie he really like, he actually emphasize the importance in terms of like what calories he like the most. Okay, so like, oh my God, fantasy, he like it. So we increase by 10, 10 here. Drama, he doesn't like it very much. So we only give 4. And he actually like the cartoon Shed, right? So we give 7 here and count this 7. And then we want to sum them up, right? Want to sum them up. So in the vertically, so 10, 0, 7, 4, 17. And then because these numbers are actually scaling, so we want to normalize them. So how do you normalize them? To normalize them, you find the sum of this. It would be 10 plus 7 plus 4, sorry, plus 17. That is a sum equal to, let's say, A. And you divide everything here by A. And you divide everything by A. So it's going to give you this number to 0 0.26, 0, 0 0.18, 0 0.11, 0 0.45. And the sum of this will equal to 1. Okay. So you might make sure that it doesn't matter how many movies they watch. The user vector have to be equal to 1. So we keep it consistent, right? Because user vector is supposed to be unbiased. Right? Imagine I watch a lot of movie, so I cannot really have like this user vector have a very large number, and one user haven't watched a lot of movies, so that user vector become very small. I want to scale them up to be equal size, to be fair. So this is our user feature vector. This is describing what? Describing the taste of the user in terms of carries. Yeah. So this user really enjoy comedy. This user also quite enjoy fantasy. This user watching quite a bit of cartoon and a bit of drama. This user doesn't like action because he haven't watched any action movie yet. Okay, so based on that, we can like, hey, this is the taste of our user, the reference. This is what he like in terms of movies, in terms of calories. It's cool. So for each of user, we calculate their feature vector. Uh, okay. Da, 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 da. Okay. So you can see that. So he watching quite a lot of drama and comedy. Eventually, after you multiply them together and you add them together, after you normalize them together, these numbers are big. It's representing he watched a lot of movie and he like it based on his ranking as well. Okay, this is the quiz again. So calculating the user vector of this user based on the ranking below. Which categories have the strongest influence of this user? Okay. Can someone do it? Okay, let's do it together. Can someone actually do it though? I actually want to give you guys like an exercise. So he only watching 4 movies, right? She only watching 4 movies. What is the categories that she like the most? She like the most. Fantasy. Okay, that's good. So everyone have the same answer. So just follow the step. Before you should come up with fantasy at home. I won't tell you the answer. You have to figure out by yourself. Yeah, just follow the step before. Don't worry. Today we have a lot anyway, so you're gonna confirm if you know the answer or not. That's cool. Okay, let's move on. If you have any questions, please ask now. Okay. If you don't know how to do it, please refer back to the previous example. It's just the same. Okay, so back to that user again, right? So he like these categories a lot. So he like what's this again? He like comedy and he like fantasy, right? This user. So we want to recommend him the rest four movie he haven't watched it. Which one he would like the most? That is the answer. So we have the feature vectors already of a user. Then you want to multiply this vector, the user vector of this user, to the movie vector. This movie vector telling you that which categories of the movie it belong to. Okay, so let's continue. So if you multiply them, blah blah blah. So you multiply this user vector to this movie categories. Eventually, you end up with this table. What does this table tell you? Let me take my note. So what does the table tell you? Yeah. So you multiply this by the first row, and you got this back. So based on the user preferences, you multiply by this movie based on its categories. This is the predicted score, how much user like it, or how close this factor to this movie. Yeah, it's like a dot product. It try to calculate the similarity between the user vector to that movie vector to see how close they are. And you continue to do it. And each of the movie give you the score. Yeah, just like this. Eventually, you want to sum them up together, give you the final score. How much the user gonna how much the user gonna like it for that movie. Based on this score, what is the recommendations? So the highest is Star Wars, and the next one is Dark Knight. And the least favorite movie for him is Memento. Okay, it makes sense though. Why? So if you go back to the what he watched, right? Based on what's the current thing, right? So you can see that he watching a lot like this movie. Definitely he dislike drama, yeah, and Memento at drama. So definitely he dislike Memento, and he actually like fantasy and comedy a lot. You can see that he give 10 for Harry Potter. So he like fantasy, and he also like comedy. And for Shed, he actually watch it, and he also okay score for cartoon and comedy. So the next thing is definitely Star Wars and Dark Knight. Why? Because for the Star Wars, it's also fantasy, which is really good because he actually like Harry Potter. And for Dark Knight, it's actually worse because it's fantasy, but it contains some drama, which is okay because think about Dark Knight got some fantasy and drama. And this guy actually watching a drama. At least he choose it. So it's combined between a movie that he actually really like it and a movie that he actually watch it. So which is okay. For the Star Wars, he actually like this because it's a fantasy. The action is not really matter because he haven't watched any action, so we assume that he doesn't like care about action at all. But apart from that, definitely Dark Knight is more influent. So what's the score again? So the score is Star Wars. Oh yeah, interesting. So Star Wars and Dark Knight pretty similar score. Mm. Oh, actually, in this case, Star Wars is comedy as well. I didn't say that. Actually, this table is changing a bit. Yeah, I think this table was swapping a bit or something. Uh, yeah, let's say this table is wrong, right? Because in this case, Star Wars only fantasy and actions. But in our table that we saw, Star Wars, Star Wars actually both fantasy, action, and comedy. That's why it's recommended most because he actually like comedy a lot. It makes sense now. Okay. Okay, actually Star Wars is comedy if you actually watch it for the plot. Uh, okay, that's cool. All right, so this makes sense that we should recommend him Star Wars and Dark Knight. And then next up, we recommend him Incredibles because he like cartoon. And the least things he like is Memento because he doesn't really like drama. Okay, that's totally makes sense. Okay, all right, next questions. Okay, so imagine that our feature vector is this of user feature. This is how what he like, right? This guy like fantasy a lot. He also like drama, and then he like actions, and then he like comedy. He doesn't like cartoon. So using this user feature vector, which movie would be your top recommendation for this user? All right, people, go for it. Remember this guy actually like the fantasy and drama. Okay, what is the answer? It's actually really easy, like just like two or three number to multiply. Okay, anyone's got the answer? The answer here is C. Yes, why? Because based on the math, right, you know that these two are super heavy weight, and this one got this already. This one is like it's got this. It's fine, but it's only got the drama. This one also got actions, and he also have like actions, right? This one is like contain a lot of things he like. And for this one, he doesn't like cartoon, so it doesn't really have. And for comedy, he doesn't like that much. It was like okay, so it's not really much. But the end was Star Wars, which I even need to calculate it. Okay, straightforward answer. Cool. So for the people who have a relationship, right? Definitely you need to like create a user feature vector for your girlfriend or boyfriend. It's can make things so easy. You can just map them into the vector, and then you can like go around and map like restaurants and shopping mall, some like features vector, and then you can multiply them using dot product to see which one that they like the most. Then you can like solving everything, you know, like your girlfriend or boyfriend asks you like, hey, where you want to eat? And then you give out like 10 different restaurants and you multiply that to her um, use a vector and give you the numbers, and you based on that you can easily know what is the restaurants to have dinner for tonight without even need to talk to her. So now you actually have the power to predict the people what people like based on what people did in the past, which is pretty cool. Okay, that's cool. Now we have little time for the lab. Let's go through that together. So what's the lab? Oh, I can open it here. So let's open the lab today. So lab for math for machine learning. All right, let's do it. So the math for machine learning. Okay, we're gonna go through this together. Yeah, quickly. Okay, let's run that. Okay, fine. Come on. Let me change that to my work, I think it's work email. That's annoying. Okay, let's try that. All right, so we're gonna use the same data set that we used back in our example, right? So we have these five movies, six movie, yeah. The Star Wars, Dark Knight, Shed, The Incredibles, Blue, and Memento. This movie is like pretty lit. I actually torrenting them today. Anyways, all right, that's not the relevant. Okay. So okay, yes. So you have for user, right? So mm, is this correct notebook? Yes. Okay. So we have for user Young, Minan, Tom, and Min, right? So we have for user. We have 6 movie, and we have 5 different categories of features. Let's print out the length of user, movie, and features. Okay, that's cool. I'm gonna save that. So this is the ranking, right? So we have 4 user and 6 movie. So the dimension is 4, 6, 4 rows, 6 columns. So 0 means that user haven't watched that movie. 1 is the lowest ranking if you watch a movie. 10 is maximum. So from 1 to 10 is the ranking for the movie. Okay. So let's say talk about Young here. Let's talk about Young here. Yeah. Um, Young here, he really like Dark Knight. He also watched the cartoon Shack, and he's just okay with that. And he watched the movie Memento. He actually disliked it. So you can see that what kind of person is Young, right? Just based on Young, you can see that what kind of person he is already. Um, and then you can bring out the thing, okay? So Young, you can see that, oh, this guy must like Dark Knight very much, okay with Shack, and he doesn't like Memento. And there's 3 movie, you haven't watched it, that's cool. This is me, I like Dark Knight very much. I also like Incredibles. I also hate Memento. Okay, it's not really real rating though. I would give this one to be 7. Anyway, so that's the idea, yeah. And then this is the movie features, right? So we have fantasy, action, cartoon, drama, and comedy. So we have 6 movie and 5 categories. So the dimension is 6, 5. For each row, this is representing for the movie categories, right? So the first movie is what's the movie? Star Wars. Okay, you can see that Star Wars is fantasy and actions. That's cool. All right, and you can bring out this map. So Star Wars is fantasy and action. Dark Knight also fantasy and actions, and a big drama. And this is the categories of movies. Cool. All right. So you have the user rating. You have the movie features. So when you apply a matrix multiplication, a dot product of these 2 matrices, you keep having okay, have to run that. Run that. Okay, let's run that. Okay, this is my user features, right? It's telling me that, hey, this is exactly what user like. So we have only 4 users, so give me 4 rows, and I have like 5 categories, right? This is telling me that how much each user like in which categories. This number is unfair because you think about it. The people who watching a lot of movies, we have a really high score, and the people only watch a few movies, we have a low score. Okay, so to make them all fair for each user, we want to normalize them, divide by the sum of that. So this user feature we divide by the sum of that, and this is what you got left. Okay, and now if you do use a sum again, it give you 1, 1, 1, 1, 1. Okay, this is nearly 1 because now after you normalize now everything you sum it, it's supposed to be 1. So now all user, even though you are old user or new user, this feature is gonna describing your personality, your preferences for each movie. That's oh shit, I did it again. But that's fine because it's 1 anyway. Okay, that's cool. Now this the first one is for Young, right? This is the user features for Young, and I want to know like which which categories he like the most. Okay, so I'm gonna sort them based on the column. So you can see the numbers here, yeah? So let's have a look at this. Let's look like that. Okay, so you can see that what is the biggest number? So 0, 1, 2, 3, 4. So the biggest number is this number. So 3. It sort the array based on the column for each row, but it gives you back the index, not the number. Okay, so this is index 3, so it gives you back 3. The second number, the second bit number is this number 0, 1, right? So give you back 1. The next one is this number 0, so give you back 0. And this is 4, and this is 2. So Young is liking this movie in terms of this order. Okay, so if I remember correctly, this one is drama. Okay, so he liked drama a lot. That's why number 3 here will going on the top. Okay, cool. And then based on that drama, you want to sort them, right? You want to plug in what number 3 means in terms of like calories. So I convert this number into the name categories. Okay, I just run this one to convert them into calories. So Young prefer drama, action, fantasy, comedy, and cartoon. And other people like me like action, drama, fantasy, comedy, and cartoon. This is how we prioritize which one they like more in terms of calories. Okay, that's cool. So we have the user features. We want to print up things out to clarify a few things. We don't really use this this sorted array for anything else. We just want to print out just to confirm a few things on it. Just to confirm this is a reference of the user. So we want to like when we want to manipulate the recommendations, we actually use the raw user feature of this. Okay, this one only showing you their references in terms of feature or vector. Now you want to recommend them, right? So we use the raw user feature that we calculate above the normalized ones. And we have the movie features. Remember the categories for each movie. You have to transpose them, right? So um, to the movie feature, it has the shape 6, 5. Why? Because we have 6 movie and only 5 calories. And this one has the shape 4, 5. You can see that 4, 5 cannot multiply by 6, 5. It doesn't match the shape, right? Because 4, 5 and 6, 5, it can't multiply to each other because 4 and 5 doesn't have the same dimension. So you have to transpose that from 5, 6, and then the output of this matrix will be 4, 6. Okay, that's what we want. And this 4, 6 matrix here is the movie feature similarity. It's calculating the predictions like what kind of movie I like in the future. Yeah, based on my user features and based on what categories for each movie. So it's give you a bunch of number. This is young. It's not this is all the 4, 6. This is the young. This is the score that young will give for each movie. Yeah, you can scan them up by 10. So the first movie is what's the first movie? Star Wars Dark Knight. Okay. So young gonna give Star Wars 0.48. You can scale them up by 10 and give Dark Knight 0.75, which is really good score. Yeah, so probably 75%. So this is predicting what score Young will give for each movie. That's cool. But we don't want to recommend them the movie they only watch, right? So what you want to do, you want to know which movie they haven't watched. So let's do this. So if I do user ranking, okay, let's go back to user ranking. What is user ranking? So this is the original user ranking, right? This is give me back what user actually ranking the movie. You can, I already tell you that all the zero here mean that they haven't watched it. So first, I want to find all the movie they already watch it. So you can do this. So not zero mean that this movie, this is list of movie they already watch it. And then you want to get this movie they already watch it and make it become zero. Yeah, because you don't want to uh, predict the score the user already give it in real life, right? You want to predict the score for the movie they haven't watched only. Yeah, so you do that, you put them to be zero. It means that, oh, so you are predicting the user score for each movie, but don't worry about the movie they already watched it because they already give the real ranking for this movie. So you put them to be zero. Okay. So what left is all the predictions for the movie they haven't watched it. For the movie they already watched it, we give zero here because we don't want to predict them. We already know the answer. And based on that, we want to sort them, right? We want to sort which movie that they haven't watched it, um, and then we'll display the movie. So let's bring out this one. To actually sort them, you can see that this is the index of the movie they refer, give them a high score. In this case, I actually include all the movie they already watched also, but you can fix it. You can add another conditions right here to remove them. That's fine. So at the end of the day, Young recommend them Dark Knight, Incredible, and Young already haven't watched Star Wars yet. So Dark Knight, Incredible, and Star Wars Memento. Okay, let's take this part and let's go up to confirm that. Um, so where's Young? Yep, Young is here. Can I move it up? No, I can't. It sucks. Okay, you can see that Young give the Dark Knight 10, give the cartoon 5. He doesn't like Memento. Uh, so definitely the movie Dark Knight was recommended. Yeah, because he already watched it. Next one is uh, Incredible. He also like cartoon. So he haven't watched cartoon. But because Incredible got similar, what is the Incredible? It's got action and cartoon. It's similar to the Dark Knight that he watched, right? So yeah, it's got some similarity here. So it's recommended. Okay, I reckon that you really need to go home if you want to convince yourself that this is a good recommendation system, right? Okay. So definitely you should remove all the movie that they already watch it out here if you want to. I just want to show you the end result, but you can remove them. Okay, so that's the whole idea about intuition of recommendation system. This is not about us need to understand exactly at every step we need to do recommended system. This is about us to see how useful is linear regressions and calculus, especially linear regressions. Um, so next up, we're gonna, so I think next week we're gonna focus on linear regressions and logistic regressions, all right? So don't worry about this if you don't understand. To see how useful is the dot product and the cost size similarity. Okay. How much time we left? Okay, I think we have barely enough. Okay, this library SciP is a collection of mathematical algorithm. I just want to introduce you guys. This is like an actual bonus library you can use to actually play around with possibility and statistic. Right? So first you can import this. And there's have a few functions you can just use to find the probability, right? Okay, so do you remember about the binomial distribution? So binomial distribution is when you have only two outcomes, yes and no, and each of them will have possibility, and you want to repeat that multiple times. What is the possibility of an event happen? Okay, for example, if you okay, so let's say the want to buy phones, right? You want to buy 50 phones in the market, and you know that only 2%, 0.2, sorry, 0.2% of the phone actually got some issue. If you buy 50 of them, what is the chance of 0 phone got affected, 1 phone got affected, and 2 phone got affected, right? So this is how you do it with the binomial distributions. This is the formula. You can say that, hey, n equal to 50. It means that I will pick 50 random sample from distributions, and I know that possibility for the event happen is really low, like only 0.002 or 2%. And this is the thing you want to use is using PMF. K equal using binomial, okay? So K equal to 1 mean that the event happened one time, so only got exactly one defected phone. N equal to n, and n is a big number, 50. Yeah, I pick random 50 phone from that distribution, and possibility for that happen is 0.002. So let's print them out, and then for k equal to 0 and k equal to 2. So I've done this. So that's possibility for all the four is good, and possibility that two four are bad. So you can see that, so if I buy 50 phone in the market, the chance that I got a bad phone is 9%. If I buy 50 phone in the market, the chance that I'm not getting any phone affected is 90%. And if I buy 50 phone in the market, the chance that I got at least two phone affected is 99%. So this is how using the library to like calculate distributions. So you can actually do like something like this. You have 10,000 phones in the market, and you pick 50 phones out of that distribution, and the P equal to 0.002, and then you can print out the sample. So I'm going to print out a sample for you. So sample will look like this. And you buy some like random phone in the market, 50, you do it 50 times. And each of them you have like two phone got affected, one phone got affected, four phone got affected, three phone got affected, four, zero phone. Based on this distribution, you have this graph. So the possibility that numbers of times you got zero phone got affected is 8 times, 15 times, 2 times, 10 times, 3 phone got affected. So this is how you play around with these library. Yeah. And you can find the mean invariant just like this. Okay, these are not so important. The important is this is how you play around with the library to get what you want in terms of distributions. Okay, now is the homework, okay, for this week. You have the whole weekend, yeah, so you can like do some, there's 2 homework for you to do it, 2 homework. Okay, so the first homework is, this is kind of like inspirational talk, okay? So imagine that you have to decide that you want to become like good at machine learning, right? You're like, hey, even though I have a full-time job, but I try to study at night. I try to attend the lectures, and I try to keep the learning every day, even though I don't have lectures on Friday, Saturday, and Sunday, but I still like try to do the homework at night every day. And let's say sometimes your improve rates at least 0.1% to 1% at most every day. So what does it mean by that? It means that on a very good day, you are really focused. After one day, you improve 1% of yourself after that day. But sometimes you're busy, you get distracted by other activities, then you don't improve much, at least 0.1% only. So that is the theory behind it, yeah. And assume that your normal distribution of your hard work is around 0.5%. That means that only 0.5%. So so the whole thing, this is the range, right? I know that my improvement rate is like from this range, but what is the distributions? So I tell you guys that, hey, it's a normal distribution, that means 0.5, and the standard deviation is 0.15. Okay, so the question is, what is the distribution of total improvement after 1 year of learning? So you have to write a Python script to simulate these situations and analyze outcome. So based on this is a suggested question that you need to answer before you can do the question. What is the range of your total improvement, mean the max? Based on the distribution of your total movement, what can you tell? What will happen if you change distribution of your daily improvement? Yeah, so this is the thing that I want to tell you that because it's a normal distributions, right? Sometimes you have the value less than 0.1%, but the question telling you that at least 0.1% every day. So this means that you have to replace all the values smaller than 0.1 equal to 0.1, and replace all the value larger than 1 equal to 1. So that's the range that we want. And normal distribution is like, could be ranging from anywhere. But all the possibility that this go out this range is low, but we need to like take care of that. Okay. Can someone tell me what is this? What is this distribution is for? Based on this graph, based on the questions. Yeah, but like this is distribution of what? Of something, right? I mean, based on these questions, based on these questions, what is this distribution for? This distribution is based on your daily improvement, okay? From 0.1% to 1%. You can see that from 0.1% to 1%. So most of the time you will be around 0.5% improvement daily, but sometimes you are really productive. You can be like up to here. Sometimes you're busy, you don't have like free time. Your improvement was like at this rate. So this is displaying the daily improvement rate distribution of yourself. That's cool, but after 1 year, right? So what the distributions? What is your distributions? Can you tell me the answer? So this is your homework, yeah? You need to like find a way to show distributions of your improvement totally after 1 year. I'm looking for numbers here. It's like the number here is like, oh, you improve 50% more after 1 year, or you improve up to 90% more after 1 year, or you improve 100% after 1 year, or you improve 200% after 1 year, improve 500% after 1 year. You think about, right? Every day you need to focus on improve 0.5%. That's really small number of what you know every day. It's increased by a little bit every day, every day, every day. It's accumulate, and after a year, what is the possibility of the total improvement compared to the first day you start. Correct. Yes. So it's between this. Yes, but remember it's normal distributions of each day. So you don't really know the answer. That's the minimum and the maximum. So there's no way you can give me the answer because the whole thing is distributions. You need to tell me, you have to show me on the graph. There's no way you can like, hey, how he improved 419%. It doesn't make sense because it's a possibility. It's not a fixed number. Yeah. Because let's say what happened if you have a lot of bad days, right? Or a bad year, so that number gonna change. So what I want to find the distributions, just like this. Instead of like 0, 0 or 1, 1 here, I want to find, let's say, oh, he most likely improved from 50% to 1,000%, for example. We don't know, right? So you need to do that. That's your homework. Think about that. Yeah. But definitely between 1.05 multiplied by 365 to 1.15. Is this 15? No. No, 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 no. So it's 0.01, right? So 1%, 0.01. Oh, 0.00, okay. 0.1% equal to what? 0.1% equal to 0.001, right? So it's between 0.001 multiplied by 365 and 0.001. Yeah, yep, 0.0. I was confused. Okay, 1 multiplied by 365. This was the wrong answer because 0.15 is the standard deviations. Yeah, it's not the maximum number. The maximum number of a day is 1%. The minimum number is 0.1%. So let's say he got a whole bad year, that every day he improves 0.1%. Well, let's say he got every day is a good year. So every day is a good day, then he got like 1% everyday improvement. And that number is correct. So between mean and max, that number. But once again, it's a normal distribution. We don't know exactly what. Okay, so the second problem for you to do homework is gradient descent. I think up by now, everyone's already like, oh my God, this again. So gradient descent is, okay, just don't worry about that term and I'll explain it in a very layman way, okay? So this is your functions. This is your functions. In theory, you could say that this is a loss function. You want to minimize that, okay? And you start as here, right? Okay, just change the column, something that's really popping, okay? Let's say you start at here, okay? You start at here. And you want to find derivative, right, of this point. And this one is a positive number. So you know that it's a positive number. I want to find the derivative. I want to find the minimized point of this function. I need to go left. Okay, so my update function would be x equal to x minus the learning rate of the derivative of the function f over the function. Okay, this is bad symbol. Let's draw again. Partial derivative. Actually, not the partial derivative. Okay, this is the full derivative of f over dx. Okay, because it's positive, then when you minus a positive, the x will go here. Okay, x will go here, and then it's going to be positive derivative. So x update to be here. And then update here, still positive derivative. Here, all good, all good, all good. And then eventually reaching here. At this point, the derivative is nearly 0. So you are reaching the target you want to reach. And the distance between each step is determined by this term, alpha. We call alpha is a learning rate. How big is your step, right? The learning rate. How big is your step? Okay, the idea here is the same, right? So if you start here, the derivative is here, and this derivative is like a negative number. Because the negative number, so x minus a negative number is plus. So x plus, so it's going to the right. Then go to the right, go to the right, go on the right. At this point, the derivative here is straight line, so it's nearly 0. So actually, it's gonna stop here, and we are reaching the global minimum. Sorry, the local minimum. This is a global minimum. We couldn't reach there, we stuck here. Okay, so this depends where you start your point. You could stop at the local minimum or global minimum based on your point. The same thing here. If you start here, clear the line. If you start here, you go down, go down, go down, you go down, perfect. You are at the global minimum. If you start here and you try to like move it, you try to move it, eventually reaching this top here, it's actually a straight line, right? So your derivative is really small, 0. And you know the rules up here, right? If x equal to x minus learning rate of something of derivative equal to 0, and the whole thing is 0, right? The whole thing here is 0. So x gonna not changing. So that's why you're stopping at this point or at this point because the derivative is 0 equal to 0. Okay. So you can initialize your x randomly between -1 and 10. Sorry, -10 and 10. And then you only calculate the derivative of the fx of these functions. It's easy, right? The derivative of this one equal to 4x minus 15 cos x. Okay, that's like super easy. And then you need to update the rules, right? So x equal to x minus the learning rate multiplied by the derivative of f at that point. So I already told you that alpha is the learning rate, determine how big your step. So you can start the learning rate really small, 10 equal 10 power -4. Okay, so and then you repeat the fx until reducing. And if you are like reaching this point and you were like jumping around, right? Because you are like trying to see, it's never reaching 0 anyway. So we are moving around here. So you want to make sure that if what you are moving is not so big, then there's a threshold, right? So if the difference between what you're moving is really small, you should stop moving. It's just like be happy then and stay there. So that is the algorithm. So let's say you are here. You are at this point. This learning rate is really small, right? So that's why it's moving slowly here. Yeah. Is it a good idea to choose a big learning rate? Can you tell me? Is this a good idea to like, oh, can I find a big learning rate so I can go faster? Is it always good to go faster? Or is it good to go slowly? What do you think? So if I change in the learning rate to be really big number, this is a good idea. It's like a car, right? It's like I go fast, like I go maximum speed. It's a good idea to change the learning rate to be really big. Why? Is there any intuition like why? So imagine I have a really big numbers, yeah, like my point, just super big number, like super big number. From here, it's gonna jump all the way here. Like, oh my god, that's I want to move right, right? I want to move right. Yeah, I just want to move right, and just like if I put extremely big learning rate, it's gonna jump here. It's like, oh, now my derivative is like positive. I should like go left, like here. It's like, oh, I should go right here. Oh, too far, go left. Oh, uh, okay. So like depend on derivative. You keep going backward and forward, backward and forward. Eventually, it's gonna hit, maybe hit, or keep jumping around. It's gonna diverge. Yeah, it's gonna like dangerous, slow, really slow. And if you say you choose a decent small number, derivative small enough, from here, you can go here, you can go here, and then instead of like going here perfectly, you go like over here. You're like, oh, okay, I go bit too fast, I go back here, maybe back here. So to choose a very big learning rate is like bad because sometimes you overshoot yourself. Instead of nearly here already, let's say you go here already, want to move a little bit over here already, you jump over the point that you want to reach. You have to go back and then you jump too fast, Sometimes you jump too fast, you keep bouncing back and forward. Uh, Maybe eventually you will reach your destinations, or maybe a good thing, right? Let's say you choose a big number. Instead of like reaching the local minimum, jump here, you miss it, you miss it. You're like, oh my God, I miss it. And somehow you have a momentum to go down to the global minimum by lucky chance. So that is like either good or bad. But if you choose really big number, then it's bad, like you're jumping around non-stop, like, oh, because your cell is so big, there's no control. It's like driving without looking at the traffic line. But if you choose a very small learning rate, so alpha equal really small, then you barely move, right? It takes so long for you to move. It takes forever to move, and eventually your computer is slow. So it's also a bad thing. So you have to choose something that, well, moderate, something in between. So that's the point of your learning rate. You have to choose something small. Okay. And why do we have a threshold? Why? Because imagine this is your okay, this is your global minimums, right? This is your global minimums. You want to reach there, and then you're moving here. This is your step. Your doing race this much. This is how much you move, right? Here, 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 here. You miss it, you go back again. You go back here again. You go back here again. So eventually, there's a point that you can never reach, right? Because you can have 0.000000006. It's nearly zero already, but because it's not really zero, you keep bouncing backward and forward at a very small distance infinitely. That's why you need to set a threshold. That's why you need to set a threshold here. Okay, draw. Yep, here. You need to have a threshold, otherwise keep like bouncing left and right, even though your learning rate is small. Okay, even it's small enough, it's still like bouncing at a very small distance forever. It could be never reaching the 0 point anyways. It's always left and right at a very small distance. So that's why you say, hey, if I couldn't really improve my threshold, it's actually small enough. If my derivative is really small enough, it's a very small number. One. Then I should stop. I should be happy and stop instead of like jumping around left and right like that. Okay, so you should set a threshold just like this. So it stop updating. It's like be happy, like hey, it's small enough, all good. Okay, that's the idea of derivative. Yeah. Okay, so you have two homework at home, yeah? This homework and this homework. I actually do think that the second question are way more important than in the first question. So if you can't do the first questions, don't worry about it. I will actually want you to focus on the second question because this is exactly the core of machine learning. Yeah, derivative is like the heart of machine learning. It's how the model become better and better and better after any training with 1,000, a million training data. That's what you call machine learning because machine actually learning what is the best way to choose to fit the model. This is idea of like the whole thing, the whole course while you are learning machine learning. So if you can do it like from scratch like that, it would be awesome. Okay, have questions? Sorry, have a question. If I start at local minimum, how do I fix that? Keep learning at 5 global minimum. Usually at this point you can't because there's no way you know that there is a global minimum or not. You already may be reaching the global minimum already. Who knows, right? Because remember your function is really complex. This is the easiest function, so you can plot them out. But in the future, your function could be like in 100 dimensions, right? It could be super complex. Um, let's give you an example. Let's find something that easy, non convex loss function. So yeah, your loss function could be this. Definitely, yeah. So your loss functions could be this. So there's no way you know that where is the global minimum without like plotting the whole all type dimension. Remember, this is only 3D. In the future, all your loss function will be like in the 50 dimensions. There's no way you can plot them here. Or like this. This is 3D only. And it's only very complex. Sometimes reaching here, you're like, hey, maybe it's already global minimum. So sometimes depends on your loss functions, optimize them to go to global minimum. But most of the time, you will learn all the practice how to like optimize these problems. Okay, don't worry about it. So for now, global minimum is good enough. Yeah. So this is called convex function. Convex functions only have one single local and global minimum the same. But non-convex loss function we have multiple uh, minimal points. Could be here, could be here, could be here, could be here. Yeah. Um, have I answered your questions? Does it make sense? So later on, you're gonna learn other advanced optimizers, which actually have momentums and learning rate decay and all of that could like allow yourself to have momentum when you go down the hill really fast. And you realize, hey, if I go down the hill really fast, then with that momentum, I can like go through the global minimum and reaching the global minimum if you have the momentum. But that is like advanced topic would be taught in later weeks, all right? All right, any questions? So you have to homework today is this one, the current descent homework and the always be learning homework. Okay, so this is your job, okay? And in over the weekend on Sunday, I will upload the solution to the Google Drive. Okay, so you guys can like have a look at that and then ask me any question if you want to. Next week, Minh Anh gonna continue to teach you guys linear regression and logistic regressions. Okay, any questions, guys? Any questions? Um, I'm not sure. I hope soon. I'm actually next week I have to take care of the full-time class. So yeah, teaching them like deep learning, which is like super advanced topic. Yeah, I hope soon. No worries. You guys in a good hands. Okay, so just continue to practice on this. Really ask you guys to finish the content design here. This is definitely like super core topic when it's come to machine learning. If you understand content design, mostly you understand like 70% of machine learning already, for sure. All right, guys, I will upload lecture recording to the uh, lecture recording spreadsheet and upload solutions on Sunday. So try your best to do your own solutions before Sunday, all right? Should be fun, yeah. This one's supposed to be inspirational, yeah? So like, that's why you always keep on learning because if you improve 1% or 0.5% every day, then at the end of the day, you would improve like a crazy amount. I would say crazy amount. I won't tell you exactly, but you're gonna improve a crazy amount of yourself. Okay, that is the power of compound interest. Okay, all right. Good night, guys. Thank you for like joining me for today. Okay, bye. Good night.